welcome back to my channel. This is day 7 of RTL Design and Verification series. Let's start Verilog coding from today onwards. In the day 6, we have seen scheduling semantics of Verilog. That is 4 regions are of event queue. We have seen which statement is going to be executed first and which statement will be followed in Verilog at the particular time frame. That is blocking assignment, non-blocking assignment, zero delay statements, $display, monitor, when actually they are going to be executed if they are in same time frame that we have seen. Today let's start coding the Verilog modules, and we need to understand Verilog modeling styles here first. Then we take some examples and then start writing the Verilog code in different modeling styles as well. Let's get in. There are 4 main modeling styles here. The very first one is switch level modeling. Here we are going to utilize NMOS and CMOS transistor circuits and how the connections of NMOS and PMOS transistors are. By looking at that, we will be writing the circuit. We will be writing the Verilog code. But nowadays we are not at all utilizing them. Why? Because it is very difficult to write a NMOS and PMOS transistor circuit or CMOS circuit for any design. Nowadays designs are very complex. Even it is very difficult to write a gate level modeling. That's why switch level modeling is very absolute. We are not at all utilizing it in a industry nowadays. Then comes gate level modeling. In gate level modeling, we should have a gate level structure for our design. Then we can look at the gate level structure and the connections between them. We can utilize AND gate, OR gate, NOT gate, XOR gate, primitives, and we can design the Verilog code. It is also not commonly used since the designs are complex and it is very difficult to write gate level structure. That's why we will be having a synthesizer that gives us the gate level structure, and we are writing the code in a behavioral style. Then comes Dataflow modeling. In Dataflow modeling, we are going to have Boolean expressions. By looking at the expressions, we can directly use assign keyword and write the Verilog code. But here also, getting all the Boolean expressions for complex designs is impossible. That's why we will be going for behavioral modeling. In a behavioral modeling, what we do, we will be using always statement, if else and case constructs of Verilog, where we are going to use multiple complex or advanced constructs of Verilog, and we are going to write complex designs. So nowadays behavioral modeling and Dataflow modeling are utilized. 90% of the code will be with behavioral modeling, and some of the statements which is much required, those cases we will be using Dataflow modeling. Then comes structural modeling style. Means if you have a complex design like this, we can subdivide into some small blocks and writing the small blocks first and connecting them together to make a complex circuit. That is how the industry works. So structural modeling says there is a structure of submodules which will be connected together using instantiation to construct a top module. This is what very much useful, and all these submodules will be designed using behavioral modeling, and some part of that will be through Dataflow modeling. By taking some example, let's write the code using gate level, Dataflow as well as behavioral modeling. Here the example which I am taking is 2:1 mux. This is very simple. We have 2 inputs and 1 output. Depending on the select line, the inputs will be available at output. If you say select is equal to 0, output will be D0. If select is equal to 1, D1 will be the output. So if you write an expression here for Y, it's look like select bar into D0 plus select into D1. This is the expression we are going to get. Now let's design this using gate level modeling. In a gate level modeling, as I said, we require gate level structure first. To get a gate level structure, let us write the expression again. Y is equal to, we have a select line here. Since it is 0, we are getting D0. It is select bar into D0 plus select into D1. This is the expression we are going to get. Now to have this in a gate level structure, we should have select, D0 and D1 as our inputs. Let me take my select as first input. I need select bar here. So I need to have one NOT gate. This NOT gate output is my select bar. Then it is AND with D0. So I need to take D0 over here. And for these two, I need to put one AND gate. This AND gate provides us select bar into D0. Then we have select and D1 together. Let me take select again and D1, and connecting these two with one more AND gate. This gives us two intermediate outputs here. we need to put one OR gate for plus functionality. This gives us output Y. This is the gate level structure we are going to have for 2:1 mux. Now, this is select signal, this is D0, this is again select, this is D1. Here we will be getting select bar. So to have select bar, let me name this as a wire. Let me take it as W1. Then we have a AND gate. AND gate output is connecting from this point to this point for a OR gate. Let me name it as wire 2. This is just for connecting between two gates. Then I need to have this as W3. Why? Because this W1, W2, W3 are intermediate connections. We can't name them or we can't refer them through select D0, D1. So these are the things required in our Verilog code now. Let's write a Verilog code for this. See, here I am using a EDA playground simulator to write the code and simulate. You can also create an account in edaplayground.com and start using it. Here I am writing the gate level modeling 2:1 mux design, and here we need to select system Verilog or Verilog as my language. So any Verilog code will start with the keyword module, and we need to give the module name as mux 2:1. Let me give the name as mux 2:1, and in the braces I need to write D0 input and D1 input and select and then output Y. These are my ports I am listing here. Then I need to declare them as input output. Input D0, comma D1, and also I have input select. Select line is my input, and I have output Y. Y is my output. So these are my input output port declaration. Then after this, I need to start using the gates, and accordingly I need to connect the output of the gate and input of the gate. So let me first take this NOT gate and let me give the instance name as something like N1. And I need to connect the output first, and then I need to write the input. What is the output of the NOT gate here? This is W1. The input is select. So here first I need to write W1 as output, and it will take input as select. But here we have not declared this W1. I need to declare the W1 as a wire. Let me declare it as wire W1, and also we require W2, and also we require W3. There are three wires here we have utilized. Then NOT gate is finished. We got a select bar in W1. Now let me write this AND gate, this top AND gate. This AND gate having a primitive A and D. Let me call it as A1, and we need to write a output first. The output of the first AND gate is W2, comma, what are all the inputs for that? Select and then D0. This is what my first AND gate is. Let me take another AND gate primitive and name it as A2. I need to name it differently. Then I need to write the output of that AND gate as W3. And what is the input for that AND gate? We have this AND gate now, select and D1. So I will take select here and D1 here. This is my second AND gate. We have one more OR gate in our design, OR. Let me name it as with the instance name O1, and I need to connect the ports now. Y is my output of the OR gate. Then I need to have W2. Then I need to have. So this is what my gate level code for mux 2:1. I need to end the module here. This is the complete code which will give you the functionality of 2:1 mux using gate level modeling. All these are gate primitives we are utilizing. Here remember, first we need to write the output of the gate, then we need to provide the inputs of that particular gate, right? So for this, let us write a simple test bench to validate whether this will work properly as per the 2:1 functionality. So for the test bench, again we need to start with module. Let me name it as TB. Here the input signals what we have become registers here. So D0, D1 are the same names I am taking, and then select is my another reg. Then outputs will be wire Y. Then after this, I need to connect my DUT, means I need to instantiate this DUT. Mux 2:1 I am supposed to use, mux underscore 2:1 is the name, and then I need to provide the instance name here. Let me write it as something like M1, or let me write it as DUT. Then I need to make the connections between the variables of the test bench and also the input and output ports of our DUT. Here how I am going to connect? First let me take D0. dot d naught of my DUT, it will be connecting with d naught of my test bench, comma, then I am connecting dot d1 of my DUT, it will be connecting with d1 of my test bench, then comma, again I am taking dot select of my DUT to be connected with select variable which is present in my test bench. So like this we need to connect all the ports of our DUT with respect to the test bench variables. Then we have y as well. Let me connect dot y to the variable y in my test bench, right? Then end with a semicolon. This is what the instantiation is. Now I need to start providing values for d1, d0 and select. Let me start initializing the values. Initial, begin. So first I need to take the value of d0 is equal to 1 tick b1, and at the same time let it be d1 is equal to 1 tick b0. These are the two values I am having. Now I am taking the select value as 0 first. This also can be represented as 1 tick b0. Then after some time delay, let me have some 10 nanoseconds of delay, then I will be having select is equal to 1 tick b1. Means we are verifying for select is equal to 0 and select is equal to 1, keeping d0 and d1 values same. Even after 10 time minutes, d0, d1 will be same. Then I need to end my initial block, then end module. This is what we are going to have in our test bench to verify this simple 2:1 mux functionality. We will be having select 0 and select 1 with these values. Let us have a $monitor statement here, $monitor. This will be keep on monitoring our outputs and inputs, then it will provide at the console. So now inside the monitor statement, let me first write a string. This string will be the values of d1 colon. I will be writing percentage b here. This percentage b will pick a value from d1 here. Then similarly, let me write the value of d0 need to be printed. First let us print d0 colon the percentage b, comma, then here we are providing d0 first, then d1. Then also we need to print the select value, select colon percentage b. Here we are going to put after that select. Then we need to have y as well. So let me include y here in the string. Y value should be percentage b. Now it will pick the values from d0, d1, select and y, and it will print over here as percentage b, means in binary. So we are going to get all binary values, and it will be printed as the values of d0 is this, d1 is this, select is this and y is this. This single monitor statement will print all the different values whenever they are going to be changed. And I will start running this. Let us see how actually we are going to get in a log. You can see here the values of d0 is 1 and d1 is 0. When select is equal to 0, we are getting y as 1. It means in this line we can observe that when select is equal to 0, we are getting y as d0. d0 will be our value 1. That's why y is equal to 1. Similarly, in the next set of values, select is changed. I am giving select is equal to 1 here. At that time, d0 is equal to 1 and d1 is equal to 0. So still we are getting y is equal to 1. Right? This is not the correct value. So we need to look at our DUT. Somewhere we have made a mistake while generating when select is equal to 1. So let's say NOT gate will be giving W1, and the first AND gate we are designing. This AND gate will take W1 and D0 as inputs. You can see here, other than select, I need to provide W1 here. Then only this AND gate will give W2 correctly. Then the third AND gate will be having select D1 and W3. Select D1 and W3 is correct, and this OR gate will be having W2 and W3 as the inputs. Here I need to provide WT2 and W3. Now let me again run this so that we are going to get the actual result. As when select is equal to 0, we should get D0 value, that is 1, and when select is equal to 1, we are supposed to get y is equal to 0, that is D1 value. This is working fine. Now if you want to have a waveform, then you need to enable this open EP wave after run. Then again you try to run, and here you are supposed to provide the dump file, right? So you can copy this from here dump.vcd need to be created. So we need to put it under initial begin and then dump values, then end this initial begin. Now you can run to get the waveform. You can see the waveform we are here. Now I need to get the signals. Let me take it from the DUT, and I can append all. Now you can observe the waveform. D0, D1, select, W1, W2, W3 also available. These three are not required. These are some intermediate signals. So by looking at the select, if select is equal to 0, you can see D0 will be available at output. So Y is equal to 1. From here, after 10 time units, we have D0 is equal to 1 and D1 is equal to 0. Because of select is equal to 1, D1 will be our output, right? This is how you can utilize the waveform viewer of the EDA playground, and you can verify the input and output signals. This is a simple gate level modeling we have seen for 2:1 mux. Then comes data flow modeling. In the data flow modeling, we require an expression, right? Again, we will be writing Y is equal to select bar will be with D0 plus select will be with D1 to get output Y. So here, to implement this data flow modeling, again I am going to my EDA playground and I am utilizing the same ports of the DUT for the implementation of 2:1 mux using data flow modeling. And let me take end module here. Let me comment out the gate level modeling code what we have used. Use slash and a star, and then at the end star with a slash. That will be commenting all the complete block of code. So here let me write it as it is data flow modeling code from here onwards, right? So in the data flow modeling, we are directly implementing the expression. So let me take it as assign, first assign, then Y is equal to, assign Y is equal to, what we need to write? Select bar. To have select bar, we need to use tilde and then we need to put select. This gives us select bar. Then it will be in and with D0, right? We can group it together. This is one expression and we will be having OR operation between these two expressions. Then again the second expression comes, that is select. It is and with D1. This is the very simple straightforward approach where if you have an expression like this in a data flow modeling. For this design also, the same test bench can be used even for verifying this design 2:1 mux using data flow modeling. Since the name of the file is same, I can use the same DUT instantiation here and I can run it directly. Again, you can see we got D0, D1, select and Y. We have multiple times here. I can delete it. So we can verify D0 is 1. When select is equal to 0, we are getting Y is equal to 1. This is working fine. Now here, when D1 is equal to 0, we are supposed to get Y is equal to 0 since select is equal to 1. This is the way we can verify the data flow modeling code as well with the same test bench. Now let us go for behavioral modeling. In the behavioral modeling, we'll be writing the code in terms of if-else statement or in terms of case statement. So again, I am commenting this code as well. Let me take a new code and let us design using behavioral modeling now. How we write in the behavioral modeling? Let me utilize the same port list and the port definitions. That will not change. And then comes, we need to have a always block here. Always at the rate, we are writing star here. Always at the rate star in the sense what? It will include all the input parameters what we have. Input port D0, D1 and select. Then we can use begin. I will be using a simple if-else statement here. That makes more sense to implement 2:1 mux. If I need to have select here. If select is equal to 1, what should be my Y? Y should be equal to D1, right? Else means when select line is equal to 0, I need to have Y is equal to D0. This is the simple if-else statement we can have. Then we can use end to end the always block, then end module to end that complete module. This is my behavioral code for a 2:1 multiplexer. This we are writing by looking at the truth table directly. You can see here select is equal to 1, D1, select is equal to 0, D0. By looking at the behavior, we are writing this code. This is what the top level description of Verilog, and it will be utilized much in industry. Let me run this code with the same Testbench now. And we are supposed to get the same kind of output even for behavioral modeling style of code. Here we have some error. You can see two errors are there. The net type cannot be the left hand side of the assignment. So output should be a register while using always block. Remember this, output should be a register, otherwise by default the inputs are wire here. Similarly, if you don't declare register, it will be treated as wire. So that is a net type. Net type we can't use in a procedural block at the left hand side. That's why it is throwing error here. So let me add reg here. Again, I am running this. Now there should be no error. Yeah, it is passing now. You can see the waveform again. Again, I am deleting D0, D1, select, Y multiple times it is showing. So D0 and D1 are same. When select line is equal to 0, we should get D0. We are getting that. Here, when select line is equal to 1, Y is equal to 0 because of D1 is equal to 0. And also you can verify in the console, we are supposed to get the same values over here. You can see values of D0 is this, D1 is this. When select is equal to 0, we have 1 as output. When select is equal to 1, we have 0 as output. I have given one more time select is equal to 0. That's why it is showing when select is 0, Y is equal to 1 as D0 is equal to 1. This is about all the three modeling styles of Verilog. Now, if you have a 4:1 mux, we need to design using 2:1 mux means this is how the structure will be. This will be called as structural modeling. So to implement this, we need to instantiate 2:1 mux 3 times in our design. And before that, we can write any modeling style of 2:1 mux, and then we need to have that 3 times in our design to construct it as a 4:1 mux. Here also you can observe to this we have a connection here that will be called as W1 signal, and here from here to here also we will be having a connection that should be named as wire W2. Let us write a Verilog code for mux 4:1 by using 2:1 muxes so that we can understand structural modeling as well. Let's get in. So now I am utilizing this 2:1 mux itself, and here only I am continuing my 4:1 mux code. So here I am naming it as mux 4:1, and I need to have a input and output variables over here as I0, I1, I2 and I3, and then my output is Y, and also I have two select lines. One is S0, another one is S1, right? This is my 4:1 mux ports. I need to declare the direction of them. Input I0, then I1, then I2, then I3, and then I have input select, that is S0 and S1, and then I have output reg. What is that output? Y. Y is the output, or we can declare it as out, since in the diagram we have taken it as out itself. So here let it be out, right? So now I need to use 2:1 mux name to instantiate it 3 times, right? If you look at the diagram here, we have M0 over here, M2 here and M1 here. All these 3 are 2:1 muxes. So now let me instantiate mux 2:1. The name of the mux is mux underscore 2:1, and let me give the instance name as M0. Then I need to connect the ports here carefully. How I am going to connect the ports now? Dot D0 of this mux connected to I0, D1 connected to I1, and Y connected to W1, and S0 connected to select. Here it is select, here also it is select, here also it is select in 2:1 mux. Now I am going to connect them together. So let's say first D0 will be my I0 here, correct, comma. Then I have D1 as I1. Let me name it as dot D1 as I1 here. Then comma. Select we need to take dot select. It will be S0 here, correct. Then comma. Output, that is output of the 2:1 mux, is now wire, that is W1 here, right. Then we need to end it. Here also we require wire declarations as signals. We have wire W1 and W2 in our design, right? We need to have W1 and W2 for connections. This is our first mux. Then I need to have a second instance of mux 2:1, and then let me name it as M1, and within the braces I need to connect dot D0 to, what is dot D0 here? This is I2. I2 need to be connected. Then we will be having dot D1 will be connected to I3. Then we have select dot select will be connected to S0, then comma dot y is connected to W2. W2 is the output of the second mux, right? Then I need to have one more mux here, that is mux 2 to 1 again, right? So let me have the third multiplexer instance here, mux underscore 2 to 1 again. Let me call this as M2 module, and I need to map this to dot D0 will be mapped to what? D0 is W1 now, right? W1 is the wire which is carrying the output of the first mux. So then after connecting D0, we need to connect D1. D1 will be connected to, what is D1 here? That is W2. So dot D1 is W2, comma. Then what is select here? Select line is S1 with respect to the 4:1 mux, then comma. So then it is output Y will be connected to out here, right? This is what the connections of all the multiplexers we have done. And let me take this over here and let me make it as D0. Yes. Then we need to write end module. That's it. This is the 4:1 mux code by using 2:1 muxes. Now we need to change the test bench to verify this 4:1 mux functionality, right? We will be having select lines, select 0, select 1. Accordingly, we need to have the test bench signals as well. So here, let me write it separately. Let me comment it out. Let us write it here, module tb, and let me name it as I0, I1, I2, I3 are my inputs as register here, and also I have S0, S1 as reg here, S0, comma S1 as reg, and also I need to have wire declarations, which are all wires here. All the outputs are wires. OUT out is my wire, right? And then after that I need to instantiate the multiplexer mux 4 to 1. So here we can implement, we can instantiate this as per the order what we have followed here. That works actually. You can see Control C. Here I am going to use this as something like M1 as my instance, or let me write it as DUT itself, and then I can have the connections like this. This is the order I am following. I0, I1, I2, I3, S0, S1 and out are the signals what we have declared here. So in the same order we can put it here like this. Then these things will be directly mapped. No need to use dot operator to connect the signals as well as the ports. If you follow the order like this correctly, then it will be directly mapped. Then we can have initial, begin. Then we can start giving the values for select lines and inputs. I0 will be equal to 1. I1 will be equal to 0. Let me say I2 will be equal to 1 again, and I3 will be equal to 0, something like this. Okay, these are my 4 inputs, 1, 0, 1, 0. Then I need to have select lines. Select is not select here, it is S0. S0 will be equal to 1. Let me start with S0 is equal to 0, and then S1 is equal to 0. Okay, then after some delay, let me have a delay here, #10. Okay, then S0 is equal to 0 again, and S1 is equal to 1. Then I have a delay again, #10. Then we need to have S0 is equal to 1, then S1 is equal to 0. That is 1, 0 case. Then again #10, then S0 is equal to 1, and S1 is also equal to 1, right? These are the 4 different cases of select lines we have. All those I am giving here, right? Then we can end this and end module. So if you want to have a waveform, you need to have these 2 lines in your test bench. So I will put it here directly so that I will be getting the waveform, right? So after some time minute, let me have some #10 again, and let me take back S0, S1 as input. Okay, then again waiting for some 10 time minute and call $finish. This will end the simulation. So here why I am using S0, S1 as 0, 0 again means, so in the EDI playground, the waveform will be showing for this at the end. We can't read it. So that's why if you have one more value, let it print at the end so that we can read this comfortably, right? Let me run this code and see if there are errors here. It will show up. We need to fix it. So you can see in line number 54, we have an error. Mixed port connection is not allowed. What is that 54? We need to see. Okay, here it is saying that the two types of module port connections by order list and the name is not to be mixed. That's why it is showing the error. So the error is that here we have dot need to be given, dot select will be mapped to S1. Now I can run this code and we can observe the waveform as well as the output. So now if you observe the waveform, for 0, 0, we are getting 1. This 1 is coming from, you can see S0 is 0 means this is I0 will be selected here as output, and here also S1 is 0, that I0 will come out as output. So I0 is 1, that is what the output we are getting. So here, now S0 is equal to 0, S1 is 1. S0 is equal to 0, we'll select this I0 again and I2 here. But S1 will be 1. S1 is 1 because we are going to get I2 as result. So in I2 we'll be having 1 again. So we are getting output as 1. Now coming here, S1 is 0 and S0 is 1. Means it is 1 0 case. So again for 1 0 case, I should get I1 or I3 as output. But S1 is 0. That's why we are getting I1 as output. I1 is 0. We are getting 0 here. Similarly for 1 1, we are supposed to get 1 is I1 and I3 will be get selected here. And coming to here, I3 will come out as output from this line. Right, I3 will be 0, so output is 0. This is how the structural description can be written by using 2:1 muxes. We have designed 4:1. So this is about today's video. Is we have seen 2:1 muxes using 3 descriptions, and also we have designed 4:1 mux using 2:1 muxes. That is structural description. This kind of design will be used in industry to design the complex designs. First we will be designing the simple circuits like this. Then we are using that to build the complex one. So we can also use mixed signal description if required in the complex designs where some functionality is out of the clock scope. Then we will be using assign statement. If instantiation is there, we will be using this kind of submodules instantiated. And then we may have some always blocks also, depending on the sensitivity list, some parameters are going to be changed. That is also possible. This is about today's lecture. Tomorrow let us see some more concepts about Verilog. Thank you.